Okay, this is the last part of roots of polynomials, and it's actually really easy once you get to understand what it's asking, but initially it's quite confusing. So I'm going to start off with a quick explanation, then I'm going to give you the wrong method to do this, and then I'm going to give you two possible good methods, and I'm going to say which one I think is the best. So here's the kind of question, and all the questions are going to look pretty much like this. I've got a polynomial, could be a cubic or a quartic as well, and it's got roots alpha and beta. Now we could find alpha and beta, it's a quadratic. Even with a cubic or a quartic we could use our calculator. I'm going to kind of try and convince you why you don't actually need to later in the video. And the question says, find a different quadratic, but this one has roots 2 alpha minus 1 and 2 beta minus 1. Now the key point here is that we have to have the same transformation of the two roots. If these were different, we're going to have to use a different method entirely. But if they're the same. So this is called linear transformations of roots, and you can kind of see it feels a bit like the graphical transformations we've done before. What we're saying is we want the roots to be 2 times take away 1. So what would that look like? Well, let's have a look at GeoGebra. So I've got this quadratic, and at the moment I've got another copy of it as well. So if I wanted the roots to be 2 times it minus 1, I want the roots alpha and beta, they could be the other way around, to be times 2 minus 1. So I'm looking for an equation that has those roots. Well, actually, I've kind of given away exactly what you would do already here. That equation is going to have those roots. And note, it's not 2x minus 1 in here. Instead, I've done this because remember, the transformation, when you're substituting, does the opposite. So just to show again, if you had the red one, the original quadratic, to get the new quadratic, you'd have to substitute x plus 1 over 2, which is kind of the inverse. So that's going to be the method later on, which, as I'm going to say, is really good. We're going to be interested in f of x. Well, actually, we're going to use w instead. W plus 1 over 2. Because that is the inverse function of 2x minus 1. Anyway, probably you've already thought how you might do this, so I'm now going to show you the bad method. This is a bad method, and I'm going to tell you why. Do not do this method. Have I made that clear? The bad method is solve quadratic and change roots. Do not do this. Anyway, let's have a go and let's see what happens. Okay, so let's solve the quadratic. So we're going to get this. Or you could use your calculator. And you would get 3 plus or minus root 5 over 2. Okay, so I have got alpha is equal to 3 plus root 5 over 2. And I'm going to say beta is 3 minus root 5 over 2. Okay, that seems all good. Right, we want our new equation to have 2 alpha minus 1. So 2 alpha minus 1 is equal to 2 times this, 3 plus root 5 over 2. Note that we want to have everything exact. And 2 beta minus 1, which is going to be 3 minus root 5 over 2 minus 1. And so I could make a quadratic which has those roots. That's no problem. W minus the first root, 2, 3 plus root 5 over 2 minus 1. That's going to be the first bracket. If W was equal to that, we'd get 0. The second bracket, because we know that we can always construct a quadratic in this way with required roots. Okay, there we go. That's a quadratic with those roots. But it's a total mess, and we'd have to multiply that all out. And would we manage to get the integer coefficients that we're looking for? Yeah, you could do it. It works, but it's a bad method. It's ugly. It's tempting to go into decimals. I'm going to show you a much quicker one. So here is the best method for doing this. So the original quadratic, we know that x is equal to alpha and x is equal to beta are roots. Well, we want the new equation to have w is equal to 2 alpha minus 1 and w is equal to 2 beta minus 1 to be the roots. What if you solve both of these equations simultaneously? You can see that w is equal to 2x minus 1 in both cases. And that's important why it would be the same in both cases. In other words, if I rearrange that, w plus 1 over 2 is equal to x. And this is the key, because I can now say that I can substitute that into the original equation. And we will get a quadratic that has the required roots where w works because of this identity. And this is exactly what we saw when we did this transformation. We substituted in to the equation. There should be w's here instead, but that's okay. So we substituted in and we get this. W plus 1 over 2 squared minus 3 w plus 1 over 2 plus 1. And this will have the roots that we require. And you can check it, because if you were to put omega, and I'm going to just do this briefly before I expand it out, if you were to write this equation out and replace it, so plus 1 over 2 squared minus 3 open brackets plus 1 over 2 plus 1 is equal to 0, then we can see that if we put into that equation 2 alpha minus 1 as w, well, this would simplify down to 2 alpha divided by 2. This would be alpha squared minus this again would just be alpha. 3 alpha plus 1 is equal to 0. And we know that's equal to 0 because alpha is a root of that original quadratic. So this is a really quick method of working. And all we've got to do is multiply out this expression to get it into a nice quadratic form. And although that looks like a bit of work, it's not bad. We can do binomial expansion so fast. I would bring out the half first, so we get a quarter. W plus 1 squared minus 3 w plus 1, 3 over 2 plus 1 is equal to 0. Okay, now we're going to multiply this all through by 4 to get w plus 1 squared minus 6w plus 1 plus 4 is equal to 0, and expand that all out. W squared plus 2w plus 1 minus 6w minus 6 plus 4 is equal to 0, and overall w squared minus 4w minus 1 is equal to 0. And that's our quadratic. I'm going to say there is a good method, and you might like this method. There's nothing wrong with using this method that uses the equations for roots of polynomials. And that is this. From our original equation, I can see that the sum of the roots must be equal to minus b over a, which in this case is minus 3 over 1, which is 3. And I can also see that if the product of the roots is equal to Well, just 1 in this case, because it is 1 divided by 1. Now, I want a new quadratic, and I'm clashing these A, B, and C's here, so that should just be 3 for it coming from the original one. But I want a new quadratic with these A, B, and C. Now, these must have the same rules. Minus b over a must be equal to the sum of the roots, which is 2 alpha minus 1 plus 2 beta minus 1. And for this one, we must have c over a is equal to the product of the roots, 2 alpha minus 1 times by 2 beta minus 1. Now you might be able to see where this is going. What we're going to do is we're going to use the things we already know about alpha and beta to help us work out what these are. Now there is quite a nice thing. You can actually make a choice to say that a is going to be 1. And then multiply everything through by a fraction or a multiplier if you end up getting fractions. So I'm actually going to just say a is equal to 1. And so we get that minus b is equal to 2 alpha minus 1 plus 2 beta minus 1, which gives us that minus b is 2 open brackets alpha plus beta minus 2, and that's, we know that alpha plus beta is 3, so we get minus b is equal to 2 open brackets 3 minus 2, and this nicely gives us that b is equal to minus 4. Over here I can say that c is equal to, multiplying out the brackets, 4 alpha beta minus 2 alpha minus 2 beta plus 2, no, plus 1. And so we can say that this is 4 alpha beta minus 2 open brackets alpha plus beta plus 1. And we know that alpha beta is 1 from up here. So that's 4 times 1 minus 2. We know that alpha plus beta is 3 plus 1. So overall, I can say that c is 4 minus 6 plus 1 is minus 1. And overall, sticking into the original equation that we had up here, with a is 1, I can say that I've got w squared minus 4w minus 1 is equal to 0, as we got before. So now we're going to have a look at what an exam question might look like on this. So it might look something like this. I'm going to do it my favourite method, and that is I can see that the transformation is the same in all the cases. Therefore, I can see that I want to, if we have x is alpha, is one of the roots, I want w to be 2 alpha plus 1. So w is equal to 2x plus 1. So the substitution I want to make is x is w minus 1 over 2. So I want to put that into my original equation, substitute w minus 1 over 2 cubed minus 3w minus 1 over 2 squared plus w minus 1 over 2 on its own plus 5 equals 0, and that's going to be, if I multiply out, the answer to my question. So all that's left to do is algebra. Now I actually think at this point I'm going to give you some good tips about how to approach doing something like this, because I think it's very easy to make mistakes. Very bad idea is just to immediately multiply that all out. Instead, what I think you should do is to focus on calculating what w minus 1 is, squared and cubed first. So I'm going to multiply everything through to get rid of any fractions. So the first step I'm going to do is to bring out all of these 2's. So this is going to be 1 over 8 w minus 1 cubed, because it's 2 cubed. This is going to be 3 over 4, because that's 2 squared. w minus 1 squared. And this is going to be 1 over 2 w minus 1 plus 5. And I'm going to multiply everything through by 8 to make sure that everything is a nice integer. So I'm going to get w minus 1 cubed minus 6 w minus 1 squared plus 4 w minus 1 plus 40 equals 0. And now I'm going to stop and I'm going to quickly calculate what w minus 1 squared and cubed is. So w minus 1 squared is going to be w minus 2w plus 1. W minus 1 cubed, using binomial or whatever method you want to use to make sure you definitely get it right, is w cubed. Now what do we get? We're going to get 3, and we're going to get 2 of the w's and 1 of the minus 1. So I'm going to get minus 3w squared plus 3w. Note that's got a minus 1 squared in it. Just take your time. And a minus 1 cubed gives me minus 1. And now I'm going to use my normal, really careful method of putting this all in and adding it up. So I'm going to put it into the first term and get w cubed minus 3w squared plus 3w minus 1. I'm going to put things in a column. So I've got minus 6 times that. So minus 6, oh, there's a squared there. Minus 6w squared plus 12w, that's minus 6 times minus 2w, and minus 6. So I'm putting this all in, and then I've got this, I've got plus 4w minus 4 plus 40, and this is all equal to 0, and then I add them all up, so I get w cubed minus 9w squared, so 3, 7, 19 plus 19w, and I've got 40 minus 11 plus 29 is equal to 0. I really recommend this way of adding together terms in a polynomial. It is so much less likely to make mistakes on missing terms, and you've been doing something like it for years. And that is my final answer to this question. All the questions look like that. It's just all about being careful about how you go about doing them. So that is the gone through an exam question there. They're all very similar. So all that's left now is to kind of recommend a few questions for you to do from exercise 4E. Okay, here's my recommended questions from exercise 4E. I think if you did 3, 4, 7 and 8, you would definitely completely have a good idea about what you're doing on this. I then really recommend you go through and do some questions from the mixed exercise. The challenges in both the mixed exercise 4A and mixed 4E and the mixed exercises are really worth having a look at, especially the one in exercise 4A. I think that looks like a definite thing to have a go at. Okay, that's the end of the chapter. I might talk to you another time a bit about kind of justifying where this goes. In particular, if I was to recommend something to look up Galois theory. Galois theory. This would be something to look up where this kind of idea goes. Also, the story of Galois is very interesting. It's a very kind of romantic and dramatic math historical event, which you may not see that many of those. So look up Galois theory, and that would be a really nice bit of reading to do. Okay, thank you very much.